Okay, thank you so much, everyone. We'll welcome everyone, and thank you so much for joining us today. We are happy that you could be here. My name is Sherry Meadows. I am a Director of Development in the College of Computer, Mathematical, and Natural Sciences at the University of Maryland, College Park. We are so happy that you could join us today for the inaugural Tobin J. Marks Lecture in Chemical Discovery. Our special guest lecturer today is Dr. Stanley Whittingham, the 2019 Nobel Laureate in Chemistry. The title of Dr. Whittingham's lecture is The Origins of the Lithium Battery and Future Challenges and Opportunities. Again, I will tell you that this webinar is being recorded and it will be sent to all registrants. Throughout the webinar, you have an opportunity to submit questions using the Q&A function that's located at the bottom of the screen. We will engage Dr. Whittingham in the Q&A discussion towards the end of the lecture, the last 15 minutes of the lecture. And now it's my distinct pleasure to introduce the chair of the Department of Chemistry and Biochemistry at the University of Maryland, Dr. Janice Root-Roby. Dr. Root-Roby.
Hello and good afternoon, everyone. I'm so pleased to welcome you to the inaugural Tobin J. Marks Lecture in Chemical Discovery with our featured lecturer, Dr. Stanley Whittingham from SUNY Binghamton. I'd like to begin by saying we are so grateful to our own Maryland alumnus, Dr. Tobin J. Marks, who established this endowed lectureship in 2016 and is joining us for this event today. So I hope Dr. Marks has his, mic that will allow him to speak. Let me just say that Dr. Marks earned his undergraduate degree in chemistry in our department in 1966. And after pursuing graduate work at MIT, he went on to a faculty position at Northwestern University, where he has had an absolutely brilliant and prolific career. He is known for his innovative and interdisciplinary research in inorganic, organic, and materials chemistry. He has won numerous awards, including the Arthur C. Cope Senior Scholar Award in Organic Chemistry, the Gabor Summerjai Award for Creative Research and Catalysis, and the 2017 Priestley Medal, which is the highest research honor in chemistry bestowed by the American Chemical Society. With more than 1,100 papers and more than 230 patents, he is one of the most prolific chemists in the world, and we are incredibly proud of his accomplishments, and we are very privileged to have this lectureship in his honor and in his name. So thank you, Dr. Marks. Please say a few words.
Well, let me begin. Thank you, Janet, and thank you to all the faculty at Maryland. I have a very warm spot in my heart for my experience as an undergraduate chem major at Maryland. It was truly transformative in terms of knowing what I wanted to do and how much I like chemistry. And I thought this was one way that I could say thank you to all the terps. Terp is a word for Marylanders. It refers to a terrapin, a turtle. And I cannot think of any better scientist today to accept this lectureship than Stan Whittingham. He's made seminal discoveries in the area of batteries over many, many years. He and his colleagues have transformed what we know about batteries and how we can use them. And they're all very much a part of our life. I remember at the announcement of the Nobel Prize, the member of the Swedish Academy who described, they have to give a brief overview of the accomplishments of the Nobelist. She went through all sorts of hand gestures to emphasize all the different things that batteries do to make our life and human life on Earth better. So congratulations, Stan. We're looking forward to your lecture.
Thanks, Tobin. And now it's my pleasure to introduce our honored guest and the inaugural Tobin J. Marks lecturer, Dr. Stanley Whittingham. Dr. Whittingham is a distinguished chemistry and material science and engineering professor at SUNY Binghamton, and as has been said, the 2019 Chemistry Nobel Laureate. He received his BA and Doctor of Philosophy degrees both in chemistry from Oxford University, where he is now an honorary fellow of the new college. He has been active in lithium batteries since 1971, when he won the Young Author Award of the Electrochemical Society for his work on the solid electrolyte beta alumina. In 1972, he joined Exxon's corporate research laboratory and discovered the role of intercalation in battery reactions, which resulted in the first commercial lithium rechargeable batteries that were then built by Exxon Enterprises. In 1988, we are fortunate that he returned to academia at SUNY Binghamton to initiate a program in materials chemistry, and where he also started a graduate program in materials science and engineering. Again, he has done so much and received many awards for this. He is presently the director of the Northeast Center for Chemical Energy Storage, which is a DOE-funded EFRC based in Binghamton. In 2012, he received the Jaeger Award of the International Battery Association for his lifetime contributions to battery research. He also received the Lifetime Contributions to Battery Technology Award from NatBat in 2017, the Senior Research Award from Solid State Electronics in 2018, and was elected a member of the National Academy of Engineering and received the Turnbull Award from the Materials Research Society. He is a fellow of both the Electrochemical Society and the Materials Research Society, and is currently the vice chair of the board of the directors of the New York Battery and Energy Storage Technologies Consortium, which goes by the acronym NY-BEST. We are so pleased to have Dr. Whittingham with us today, and I will very much, as you all do, look forward to the seminar. So I'll now turn the webinar, the virtual podium, over to Dr. Whittingham.
Thank you very much. I hope you can all hear me okay. Yes?
Yes.
Great. So what I'd like to do is go back essentially 50 years and show you how things started. But before I do that, let me just recognize the US Department of Energy, who supported my research for the last 30 plus years. So I need to thank what was then SO Research, who I joined in 1972 in their brand new corporate research labs, which gave us the freedom to look at a whole lot of new science from a fundamental point of view, and who, towards the end of 1972, agreed after I spent, I think, about 10 minutes in their New York office talking to a subcommittee of their board of directors to support an effort in lithium-ion batteries. They treated research in those days like drilling oil wells. Maybe 10% would be successful, and the same thing with the research. They were willing to take big risks and hope things would work out well. So I show you some pictures taken from that period. And you can see I was just a few years younger then, and you'll see that men's clothing does change, wide lapels, wide ties in that period. But in the middle, you'll see the single crystals of titanium disulfide we used, and I'll describe this a bit more later. And recently, people have gone to powders, but now there's a swing back to single crystals because of the lower surface area and less reactivity. On the right-hand side, I show you two battery systems. The upper one is one we built as giveaways to potential customers, has a lithium-ion battery on the left-hand side, a watch on the right-hand side, and a little solar cell underneath. This one still sits next to me here in my home office, and it's still working even though it's 40 years old. Beneath that is a rather large battery we built for the electric vehicle show in 1977. This one is about 6 inches tall, 4 inches wide, and about 1 inch thick. And this turned on and off a motorcycle headlamp for the whole week of that show. And that was really the beginning. I said this was about 1976, 77. And we managed almost exactly a year ago now, Bob Hamlin, who led the development and manufacturing effort, and I searched in our basements and we managed to find some of the old cells. So this larger one and the small button cell now sit in the Nobel Museum in Stockholm, together with the sales brochure that Exxon put out at that time. So Exxon was very serious about getting into alternative energy, fuel cells, solar cells, batteries, and they were planning to build electric vehicles at that point. So let's look at what was special about the layered sulfides we looked at. Initially, we were looking at these as superconductors. In fact, we looked at tantalum disulfide because by intercalating electron donors into the structure, we could change the superconducting transition temperature. Once we found out they were potential electrochemical devices, we switched to the lowest weight one, which is titanium. And it turns out this material, besides having a layered structure as shown here, these are the titanium disulfide sheets. In between these reside the lithium. And anybody who knows the thermodynamics knows that ambient temperatures, entropy plays a role. So there's always some distribution of titanium from the titanium sheet down to a lithium sheet and vice versa. And it turns out that it's about 1 or 2%. This is advantageous because it stops these sheets from moving relative to one another. The other big advantage of this particular material, for practical purposes, it shows metallic conductivity. So in a battery, you need to get electrons in and out as well as move lithium ions. So in this case, we do not need any carbon black to increase the conductivity. It also is single phase. So it has exactly the same structure with no lithium in it and up to 1 lithium. So no energy is expended in nucleating a new phase. And I show you a typical discharge curve. It starts out about 2.3 volts, ends up about 1.8 volts. And the slow decline in the voltage is due to the conduction band being filled with the electrons. So you get less and less energy out of it. On recharge, you can see the curve follows exactly the discharge one. The difference here is just the resistance loss in the electrolyte. And I should emphasize this was run at 10 milliamps per square centimeter, much higher than any lithium-ion battery is today, and that's partly because of its metallic conductivity. So another advantage of it being metallic conductors, the reaction can occur at all points where the material touches the electrolyte, not just where material, carbon black and the electrolyte are in contact, so we get much higher reaction. I'd like to acknowledge my team here, Art Thomason, who was a physicist, John Pinella, who was my technician, Russ Kennelly, who is a crystal chemist and is now at UT El Paso, Alan Jacobson, who was a solid state chemist from Oxford, who's now at Houston, Marty Dines, who was our organic chemist, Bernie Silbernagel, who was our NMR expert, and Fred Gamble, who was initially the group head and whose interest was in superconductivity. And finally, Al Schriesheim, who was our lab director. And after he left the corporate labs, he went to engineering. And probably many of you know that he then led Argonne National Lab as a very successful lab director. I mention these names because of the students in the audience. We all had slightly different backgrounds, so we all came to the challenges in a slightly different way. And this is what made us successful. Now, titanium disulfide worked well with lithium. We obviously stopped work on this at some point, but this is still a model compound. So if we look at today's work, Linda Nazar and her team used titanium disulfide as the cathode for a magnesium battery. Because it's a metallic conductor, the electrostatic interactions are shielded, so the magnesium ions can diffuse fairly readily through the lattice. And you can see the cycling curve here. Very little polarization. There's 40 cycles here, essentially 100% Coulombic efficiency, and very little fall off in energy as it cycles. But you'll notice the discharge potential now of magnesium about 1 volt less than that of lithium. So even though it cycles well, it is not really a realistic battery system long term. And you'll notice it's also run at 60 degrees centigrade compared with the 21 for the titanium disulfide. Other folks are now looking at calcium diffusing in this material. So again, this soft covalent lattice lets a lot of ions diffuse much more readily. It's also been studied lately as an electrochemically active substrate in lithium sulfur batteries. In the examples I show you here, this is vanadium disulfide, essentially the same structure. On the left-hand side, this is a non-aqueous electrolyte. And you can see getting over 800 milliamp hours per gram, very high values here, and not too much polarization. And you can see the cycle behavior is very good here. And this is for different ratios of sulfur to the vanadium disulfide. On the right-hand side is more work from Linda's lab. And this was an all solid state cell. And you can see there's obviously more polarization because it's solid state. But again, she got more than 50 cycles out of this. And it helps having this electrochemically active substrate so the vanadium disulfide can intercalate the lithium as well. So people said these layered sulfides are not dead yet. There's still a lot of interest in them for basic research. Let me, just in case there's anybody in the audience who doesn't really know what a lithium-ion battery is, every battery has an anode and a cathode, and in between an electrolyte. In a lithium-ion battery, you have lithium ions stored on one side when it's fully charged. When the battery discharges, it goes from an organic electrolyte into the cathode material. In the case of our initial Exxon work, this was pure lithium, and this was titanium disulfide. And in between here, there's a lithium salt, obviously an organic solvent, because aqueous solutions don't work there. So let's look at now a little bit of the history. If we look at back in 1972, when we started this work, we used lithium, then we switched to lithium aluminum, and I'll show you in a moment why we did that, because all of today's so-called lithium batteries are in fact lithium-ion batteries, with one exception: none of them have lithium metal in them. Lithium aluminum cycles well for maybe about 10 cycles. It's a very brittle material, so crumbles eventually. Akira Yoshino in Japan replaced this with graphitic carbons, and that's what was used in the first batteries of Sony's in about 1991. And this is in fact showing this graphitic carbon in here. The problem here is you need 72 grams of carbon for every 7 grams of lithium stored, and it takes up half the volume of the cell. So eventually this has to go, and there's a lot of research today replacing with tin or silicon, both of which react with more than 4 lithium ions. And really the goal of many of us is to go full circle and go back to pure lithium. If you now look at the cathode side, we started out with titanium disulfide. John Goodenough, who was at Oxford at the time, working on the magnetic properties of lithium cobalt oxide, read our work and realized the structure was the same. He tried this out with his students and postdocs and As you all know now, it worked. Chemists would have said it wouldn't work. You can't make cobalt-4. John tried it and it does work. Since that time, and I should say this material is still used in all your cell phone, laptop batteries because it has the highest density and therefore the highest capacity per unit volume. But cobalt is expensive. It's also child labor issues in the Congo. So people are trying to take all the cobalt out. So we now have materials made of nickel, manganese, and cobalt, or in the case of Tesla, nickel, cobalt, and aluminum. Some years ago, John then came up with these, what we call olivine structures, lithium iron phosphate. These are obviously all abundant elements, therefore lower cost in principle. And this has been used in the US for some grid storage and is the predominant cathode in most of the Chinese vehicles. At Binghamton, in a bigger factory we hope to build here within the next year, we'll be switching out most of the iron for manganese, which raises the voltage. But the energy density of these phosphates is much lower than the oxides. So it has restricted usage. You're not going to find them in your phones or in your laptops. So what we're looking at now is, can you solve that by reacting more than one lithium with the transition metal? So at the end of this talk, I'll briefly discuss how we've shown proof of principle that you can in fact intercalate two lithiums into a lattice without that lattice being destroyed. But let me show you a few applications of lithium-ion batteries. Whilst we're in Stockholm last December, two of the physics laureates and myself, we talked to these two astronauts on the space station live. The lady here is an American from state of Maine, and her mother is from Sweden. And the fellow on the right is from Italy. And they just replaced the nickel metal hydride batteries on the outside of the space station, which are used to store the solar energy, with lithium ion batteries. And they were very pleased because they were half the size, weighed half as much, and were planning to last twice as long. So that was one successful accomplishment. But I think you all recognize all the different applications of lithium-ion batteries. Probably everyone in the audience has got at least one on their person, if not more. So here are a couple of smartphones. I'll come back to the environment a little while, but clearly lithium-ion battery storage is enabling renewable energy, including solar and wind storage. And this is a wind farm in Western Virginia, and I think this is 32 megawatt hours of storage here, which smooths the wind energy and can shift it up to about 8 hours. Then I show you a series of vehicles on the right. This is a two-wheeler electric vehicle that my wife and I rented in Bermuda 18 months ago for our 50th anniversary. And they were just introduced to the island, and these are the only cars that visitors are allowed to rent. So we rented it and were warned, if you drive to the far end of the island, you will not be able to get back, but there is a recharging station there. So we drove to the far end of the island, went to the recharging station, and they were still building it. So fortunately, partway back, we did find one where we could recharge it. We went and had dinner whilst it was being recharged, and they got back. But this is kind of the small end of the vehicles. I show you on the right here a group of 4 other vehicles. 2 of these are Peterbilt vehicles. This is Washington State. They have a test track there where they develop these vehicles. This one is a 16-wheeler, and you can see all the lithium batteries here. This particular truck is now in the Los Angeles docks and takes containers from the ships to the local distribution points. This is very important because today, mostly the oldest, dirtiest trucks are used for that purpose. And on the right here, you'll see a garbage truck. And this is an ideal use for electric vehicles, it's stop, go, and raising, lowering the whole time. And I was fortunate enough to be able to drive these around their test track. Whilst we were in Sweden, the UK ambassador brought 2 electric vehicles over from England. The reddish one here is a Jaguar all-electric vehicle, and on the right, a London taxi, which was jointly built with Volvo, and these see active service every day in London. And she, in fact, used the London taxi to go to and from the palace. So Britain is taking electric vehicle and clean energy extremely seriously. So let's look at where we stand today, because a lot of people said, well, now the Nobel Prize has been given out, we're all finished with lithium-ion. And we have to correct them and say nothing could be further from the truth. Today's batteries don't even attain 30% of their theoretical volumetric capacity. And it's about the same on a gravimetric basis. And you can see some of the numbers here, don't worry about all the details, but this percentage here is the percentage the natural battery gets of its theoretical volumetric capacity. So it varies from 11% to close to 25%, and the gravimetric is around about 25%. So it's still huge opportunities for improvement. And I'm part of the DOE Battery 500 Consortium, and our goal is to get this number up to 50%. To do that, we have to do a number of things. One is we have to get rid of most of the carbon. So I mentioned a moment ago, it takes up half the volume of the cell. So we either need to make lithium metal work, or in the interim, make silicon or tin work. In addition, we need to use all the lithium in the materials. In these layered oxides, we use about 60% at the moment. In the phosphates, we need to better put 2 lithiums in there. But we need fundamental research on how to increase the ionic and electronic conductivities of these materials. We could then make thicker electrodes, so we reduce the amount of current collector and separator. So let me just discuss the anode first and explain what we did initially. So lithium metal itself was used in the first generation of the Exxon cells. Moly Energy went commercial. They used molybdenum disulfide instead of TiS2. They used lithium metal. And after a number of their batteries, which were used in the black boxes and the planes, almost brought the planes down, they stopped using lithium metal. But this is what happens. In any metal deposition process, you tend to get dendrites formed. And this was work of Russ Kennelly, who's now, as I mentioned, in El Paso, at the University of Texas there. And this was one of the first operando studies in an operating battery. As soon as you get a little protubration like this, then the electric field between this tip and the other electrode is increased. So once they start, they grow fast. And this will grow through any separator, even if it's a polymer, or even through the grain boundaries of ceramics. So there's a big issue on these dendrites. And you can see the effect on this booster station that AT&T had in some housing developments. These were built by Avistor in California, in Canada rather. They used pure lithium anode. They used a solid polymer electrolyte, and they used a vanadium oxide cathode. They made the polymer too thin, so the dendrites grew right through it. And these lasted maybe a few months before they were all pulled off the market. So an intermediate option to going to pure lithium is to go to tin or silicon. This will double the volumetric capacity. So if you look at the plot at the bottom here, everything is relative to carbon. So here's the volumetric capacity relative to carbon. So you can see if you put 2 lithiums into tin, we can more than double the volumetric capacity. And you don't need to go all the way up to 4 to get the advantage. You don't need to stress the lattice that much. If you go as far as 4, you more than double the gravimetric as well. And you can see these materials have essentially the same volumetric capacity as pure lithium metal. Sony, in fact, commercialized in about 2005 what turned out to be a tin cobalt alloy anode. This is in one of the camcorder cells. Clearly not commercially viable, even though they were selling it, I think, for about $100 a battery. So we decided we'd try to replace this with iron. So we made some some iron tin compounds. And I think I recounted it to some of the students earlier. Tin itself is not viable. It expands 300%. So we try to protect the tin with carbon coating. So we ground up tin with carbon. But we're using iron balls and an iron vessel. And what we landed up making was this tin iron compound. We made it stoichiometrically, beautiful X-ray pattern. And this is all done basically in a grinding media. And you can see the cycling behavior here is the black one is graphite. And you can see why people like it. It's absolutely stable for 1,000 or more cycles. But its capacity is only about 0.8 amperes per cc. Our tin iron material is more than double that, and even after 140 cycles, it's still double. So this is proof of principle that an alloy will work, will give us good behavior. And just for those of you not familiar with this area, battery scientists talk about C rates. A 1 C rate is a battery that's charged or discharged in 1 hour. A C over 10 is 10 hours. And the typical automotive battery, you test at C over 3, so that's a 3-hour rate. So let's look at the cathode now. And as I mentioned earlier, most of the materials used today are these layered oxides. They replace the sulfides. And they have essentially one lithium in them, the common ones. Then they have a mixture of elements, typically nickel, manganese, cobalt, and invariably a little bit of aluminum to stop you charging these all to the +4 state, these stabilizers and materials. And you'll see this lettering here, NMCA, commonly used. The pure cobalt analog is in most of your electronics, but the mixed metal ones dominate everywhere else. And today there's a major effort to eliminate the cobalt, both because of cost and environmental issues. And reducing the amount of cobalt means you've got to increase the nickel or manganese. And it turns out the reaction rates are poor if you increase the manganese. So most people have gone from a equimolar mixture of nickel, manganese, and cobalt to this 60% nickel. And I put the formula at the bottom here. And this is what's in today's vehicles. And the goal is to go to 80%. There's a big challenge here because the more nickel you put in these materials, the more unstable they are. So all these materials, if you pull out all the lithium, metastable at room temperature, and if they get warm at all, will evolve oxygen. So let's look at the most stable one of this. This is 1/3 nickel. This is stable to about 310 degrees centigrade. It only stores 160 milliampere hours per gram. If you go to 85% nickel, you're approaching 210. But now you see here, this thermal stability is only 220. Clearly, we're not going to heat the battery up to these temperatures, but this instability is a measure of how fast these materials react with the organic solvent, so are reflected in the capacity retention. So our goal is to get to this upper box here, highest energy density, highest stability, and retain capacity forever. So one of the means of addressing the reactivity is a little bit of aluminum magnesium helps. it doesn't you make a 10 or 20 degrees centigrade improvement, but it reduces the capacity. Manganese is much more thermodynamically stable and it's lower cost, but its rate capability today is not good. So let's just look at some of the initial data we got from our consortium. This is the Battery 500 Consortium, which is a DOE consortium run out of Pacific Northwest National Lab. So what we did, we bought a large quantity of these materials from a commercial source. So everybody in the consortium worked on the same material. It was thoroughly characterized. We found single phase good material, the chemistry was good. So my ex-student Jay Xiao built batteries of this material, which were then tested at Idaho National Lab. And you can see the stability of these materials is very, very good. And these exhibited 350 watt-hours per kilogram at a cell capacity of 2 ampere hours. And this was really the goal of the consortium for its second year. And there's no fudging the data because these are pouch cells we used. These were weighed and the volume measured, so we know exactly that these are real data. And for those of you asking, well, what's the volumetric energy density of this? It's about 700 watt hours per liter. So these cells are the highest energy density lithium-ion batteries made today. They're not commercial because we're still very much worried about using lithium metal, particularly in large cells. So to get the energy density still higher than 350, we need to go to even higher nickel contents. So we looked at what's the impact of changing, say, from 622 to 811, and we found it, in fact, was superior in every way. And don't worry about all the details in this plot. All you need to see is this is different rates. The rate capability falls off much faster for 622 than for 811. And this is done for different loadings of the material from about 6 milligrams per square centimeter to about 25. And the loading has much less effect on the 811 than the 622. So we've, in fact, program has switched over to the 811 material now. But the challenge here, as I say, it's less thermally stable, but it's also much more reactive to the air. So this material has to be handled in a dry room or glove box. You can't handle it in a regular atmosphere. So it has to be, after being manufactured or prepared, it has to always be stored in an inert atmosphere. So with this material, we have in fact achieved 400 watt-hours per kilogram over about 100 cycles. And this was goal for this summer. So that was achieved. But what we have to do if we want to get even higher, as I mentioned earlier, we have to use all the material. So a big challenge with all these layered oxides is what's called a first cycle loss. And this is about 10 to 15% depending on the actual cell. And I'll show you a cycling curve here. Here's the charging up to about 4.4 volts, which is typical for us. Commercial cells are about 4.2 to 4.3 volts. When you discharge it, you do not recover this last 30 milliampere hours per gram. So this is permanently lost. And this is capacity at the low voltage where the electrolyte is more stable and we should not have any problems. So it's essential that we recover it. And I should point out all the commercial materials today use what we call meatballs. So these are 100 to 200 nanometer primary particles joined together to form these from about 10 to 20 micron secondary particles. And in a commercial battery, it'll have this size particle plus some smaller ones so they pack even more efficiently. So we wanted to know what caused this and how could we solve it. So my students looked at a whole lot of different parameters, and these are basically parameters that we found were not important. And this was somewhat of a surprise. So the loading of the active material was not important. So this is going from 6 milligrams to 20 milligrams, exactly the same. Even more surprising, the actual nickel content had no effect. So with the lowest nickel content, you get less capacity. So you see with 80%, you get more capacity. That's one of the reasons for going here. But you can see in the end, you don't gain anything. But I should point out here, you're seeing now this little step here. What we're doing here is after a constant current charge and discharge, we're now holding it 2.8 volts. And you can see we're getting some of this capacity back, which is suggesting to us this is a rate limitation. We then looked at different sorts of carbon, acetylene black, graphene, this specialized C65. Again, no difference. And it made no difference how much carbon we had in there. So this is the amount of carbon, amount of binder, and the active material. So whether this was 2% or 10%, it did not affect the capacity of the active material itself. So these were not important parameters. So what is important is something that we call calendaring. So let me go over to the right-hand side here. This is a typical charge and discharge. So this is charged at C/10, so this is 10 hours. So all lithium-ion batteries are charged and discharged at a very low rate, typically C/10 or even lower, to break them in and to form protective layers. It's called SEI films for the first few cycles. So this is where we get this first cycle loss. If we calendar it, what that means after making the electrodes, we put it between two rollers and squash it flat. And this is a few tons per square centimeters, a very high pressure. You can see we've got part of it back. So making better contact helps. If we now take the first one, then just do this constant voltage discharge, you see you get quite a lot more of it back. And if we're calendaring and do constant voltage discharge, we get even more back. So all of this suggests that it's slow kinetics. And our colleagues at San Diego charged these to different amounts, like 20%, 30%, 40%, 50%. And this first cycle loss was exactly the same, which suggests that it's the last 10% of the lithium does not easily go in. So let's just look at what we in fact did. We then measured the diffusion coefficient of the lithium in these materials. So the black circles here are in diffusion. So you can see this is quite high to begin with, about 10 to the -9. Once you get above about 80% lithium, it then falls off by about 4 orders of magnitude. So tremendous fall off here. And Anton van der Ven at Santa Barbara has argued that this is due to the diffusion mechanism. In this material, the lithium ions jump from one octahedral site to the next octahedral site, but they have to go through this middle site, which is a tetrahedral site. To make that jump, they want this other octahedral site to be vacant. So you've got to have this die vacancy mechanism. And clearly the number of die vacancies falls off rapidly as the lithium content increases. Putting the lithium in, there's very little change in the diffusion coefficient. So, taking the lithium out. So fast charging of this material, there's no issues at all. And further evidence that kinetics was the key issue is here's room temperature data to 4 different charging voltages, 4.2, 4.4, 4.6, and 4.8. You'll see the charge and discharge curves here are starting to separate. This means we're actually reacting the material with the electrolyte and forming resistive films. And on the right-hand side, you can see what happens when we raise the temperature to 45 degrees centigrade. This first cycle loss is reduced dramatically, and this red one corresponds with this one here. So a big drop. At 4.6 is also drops. But you now see we're getting this hysteresis getting larger. At 4.8, in fact, we get a larger loss, and this is because we're actually getting reaction of the material and forming salt-like films on the surface, and you can see this much larger polarization. So these materials are not stable at high voltage charging if the temperature is elevated. So we were looking at how do we solve this, and there's several clues. One is cobalt oxide has essentially exactly the same structure. It does not show a first cycle loss. So let's look at these two plots on the right-hand side here. Here's the black curve. This is 80% nickel at room temperature. The red one is 80% nickel at 45 degrees centigrade with this constant voltage discharge. You can see both of these, since you get back to the original position, and these were held for 100 hours. So again, this is saying kinetics is an issue here. Cobalt oxide, in contrast, you see the blue is room temperature, this purple one is 45, and there's essentially no difference. So kinetics is not an issue here, which told us if this little bit of temperature change can make all this difference, then we ought to be able to modify the structure or the electronic behavior to eliminate this difference and make these mixed metal oxides behave more like the layered oxides. So what we did, we decided to modify these layered oxides by either substituting elements inside it or by coating it. And our initial studies, we used a lithium niobium oxide solution, which we soaked the meatballs in, and then we fired the materials up to about 400 degrees centigrade. And what you now get is a niobium containing layer on the outside. And this goes into the bulk of the material, just a few nanometers. The center is left the same. And you can see now here, the black line is pristine material, no niobium, and putting 1% or 3% in, cut this by about 40%. So just 1% does a trick. We're now trying to get it so it goes all the way back to the original. So we think it's possible to eliminate this first cycle loss. This will let us get the capacity still higher, and does it at a voltage regime where the electrolyte is not threatened by decomposition. So let's look at some opportunities for future studies. I said we started out with titanium disulfide. Moly Energy in British Columbia switched to molybdenum disulfide because this is a naturally occurring ore in British Columbia called molybdenite. They said they made batteries commercially for quite a long time, but had problems with the lithium anode. The field then switched to lithium cobalt oxide, then to NMCA, and then the field moved to lithium iron phosphate for low energy density applications. And it's interesting, this material, which has this tunnel structure where the diffusion is essentially in one direction, shows no first cycle loss, as we show in the plot beneath here. These essentially lie on top of each other. So again, it's a clue we should be able to do it. What is interesting, this particular material is probably the highest powered cathode known, even though it's an electronic insulator. So it can be made to react fast, and we did this by making this into a single phase reaction. But it has too low an energy density, so we are hoping to commercialize a manganese equivalent of that, which gets it up to 4 volts. But the real interest we've been looking at is, can we make a two-electron redox system. And we chose vanadium because vanadium can easily go from +3 to +5 oxidation state. And we had some clues earlier on this might work. And despite a lot of people's concerns about is there enough vanadium in the world, there's more vanadium in the world than there's cobalt or nickel or copper. So it's the fourth most abundant transition metal. So I really discussed most of this already. Other advantage of looking at this material, there are at least 7 different variants. And so we wanted to look at the different structural types. We had the option then of using 2 lithium, 2 sodium, 1 magnesium, or 1 calcium. Here I'll only talk about the 2 lithiums. I will mention that our colleagues at Toyota looked at our material with magnesium, and you have to realize magnesium is, I call it the sulfish element. It goes to the structure and says that oxygen ion is mine, and it takes it out and forms magnesium oxide. So let's just look at this structure briefly. We're looking at mostly at the epsilon variation of this material. And this is a material first made by Alan Jacobson at Exxon. These materials are good oxidation catalysts in the chemical industry. And I'll show you in a moment, this is causing us some problems. But this is again a tunnel structure, so it's very, very stable with phosphate tetrahedra and vanadium oxide, very strained octahedra. So we have this nice tunnel structure. And we spent a long time trying to make this material. And in the end, the student found a good way to make it electrically active. And she made this by a route that we've been pursuing for the last 25, 30 years. This is what we call a soft chemistry synthesis. It's about 200 degrees centigrade. We can use water, or in this case, we used 95% ethanol with vanadium trichloride and phosphorus pentoxide. You cannot use pure ethanol because it will reduce the vanadium too far. But this reaction is easy to carry out. The pressure in this reactor just comes from the solvents, so we don't put any external pressure. And this temperature is a typical waste heat temperature in a chemical plant or refinery, so it's essentially free. So after this reaction, we made the 3-dimensional structure. It has protons inside the lattice. So this was our goal, the 2 lithiums. With protons in here, a mild heat treatment of this material for about 3 hours removes the protons, or we can in fact build an electrochemical cell and electrochemically pump the protons out. And what Kerry Sue, who was my lead student on this, who's now at Argonne National Lab, was able to synthesize these little cuboids. They're about 100 to 200 nanometers in size. Very uniform. A lot of our earlier synthesis gave us micron-sized particles. These were not very reactive. And when we used grinding to reduce their size, we in fact changed the coordination number of the lithium and the vanadium in there. And this was Claire Gray's work at Cambridge, who said, you're doing damage to the materials. That's why we went back and made these very pure materials. Now I should emphasize this was done by our Nexus EFRC joint effort between experimentalists, theoreticians at San Diego, characterizers such as Claire Gray and Karina Chapman and others at APS and Stony Brook. And this is the electrochemical data we get out of this material. This is the vanadium 5, vanadium 4 redox plateau. Here's the 4 to 3. And you can see we get some ordering of the lithium ions in here. And it reproduces on the recharge. And the important thing to note here, the first cycle is in black, the 50th cycle is in purple, and there's essentially no difference between these. So we got proof of concept that you can stuff two lithium ions into a crystalline lattice without destroying the crystallinity of that lattice. However, there are still some challenges with this material. The kinetics in the two voltage plateaus are quite different. So let's look at the high voltage region first. This is this one at about 4 volts. Here's C over 50, so this is a very slow rate discharge. So it's 50 hours. Here is 1 hour, and you can see we're losing capacity very fast. So this is slow kinetics, and we show the capacity as a function of the rate in here. And what we've determined in this particular material is a two-phase reaction. So we got vanadium phosphate in equilibrium with lithium vanadium phosphate. So we have to nucleate this new phase, and we're hoping to, in fact, turn this into a single phase reaction. But at the moment, this rate limiting step is limiting the material. In direct contrast, though, in the low voltage region, this is below 3 volts, just below 2 volts. What we do here, we discharge it, it's the 5 to 4 into low voltage. Then we cycle backwards and forwards in this region. And you can see here we have black one is C over 50, the purple one's the C rate. So the capacity doesn't change when we go from a 50-hour rate to a 1-hour rate. So it's extremely high rate material, and this is because we got a single phase reaction throughout here. We're not nucleating a new structure. But we do have challenges in this material. At high rates, what we say is the coulombic efficiency is very good. So we get out the same number of coulombs we put in. But at low rates, we're putting in more in than we get out, but we're getting the theoretical amount out. And I should emphasize, in these materials, we have got the theoretical capacity. So on charge, we're getting another reaction going on. And we now know this is the vanadium phosphate is electrocatalytically oxidizing the organic solvent. And there's some protons going into a lattice, which are then evolved. So we've got an oxidation reaction going on here. It doesn't damage the cathode at all, but clearly is not a viable approach going forward. So we have to solve two problems to make this material viable. One's the high rate capacity at the high voltage, and the other one are these side reactions. So we're looking at different solvents to do this. To conclude on what's really next, number of people saying, well, what's beyond lithium ion? I think the consensus in the field is that lithium ion will dominate for the next 5 to 10 years. And I didn't show you the slides of what's happened to the cost of these batteries, but they've dropped from over $3,000 a kilowatt hour 5 to 10 years ago to what's today about 110 and predicted in the next 2 or 3 years to be about $50 a kilowatt hour. So any new systems clearly got to get to a lower cost. So the layered oxides are going to dominate. These will probably have less than 10% cobalt and a good chance of no cobalt in them. The phosphates will have key markets. And if you listen to Tesla's Battery Day, they will use the lithium iron phosphate in most of their Chinese cars and in their so-called $25,000 American car, which use the lower cost lithium iron phosphate. The big challenge here is we need a safer and more stable electrolyte. Today's lithium ion batteries are still using the same carbonate electrolyte from the 1990s. And I think the real interest is, can solid state succeed? Can it give the required? Oops, we had a little problem there. I'm on the last slide. Go back to there. Can it give the power densities? This will let us use lithium metal. And I think we're going to be hearing interesting news shortly from Quantum State in California. The big thing I think energy storage is going to help us do is mitigate climate change, make a better environment. It's going to let us have greener vehicles. It's going to enable renewable energy and eliminate dirty peaker power plants. These are power plants that use maybe 1% to 10% of the time. We had one of these just 2 miles from the university. They put a 8 megawatt hour lithium-ion battery in there. Within a month, the power plant, the coal power plant, went off and never came back again. So I just want to leave a message with you. We need to leave a greener world for our children and grandchildren. And with energy storage and renewable energy, we can do that. Thank you very much.
All right, thank you so much, Dr. Whittingham, for an excellent talk and lecture on chemical discovery. I think about where we would be in this pandemic without portable electronic devices. And this discovery in the 70s that you made on rechargeable batteries has certainly helped us deal with this pandemic. So thank you. We have a great mixture of questions from faculty and students. And I'm going to try to go through them. If I don't get through all of them in 15 minutes, I apologize. Okay, so the 811 NMC compound, you achieved great capacity there. What were the design principles in choosing this compound over the 622, or was the result from a combinatorial experiment?
We were aware both our work and the work of many others, particularly a South Korean group of Yongkok Sun and Jeff Dahn. Now, the more nickel you put in there, the higher capacity you can get to any given charging voltage. So if we wanted to go to 400, we had to increase nickel content. So it was a logical step. You didn't need to do combinatorial. I think there's probably some combinatorial going on now to get the right mixture of nickel, manganese, cobalt, aluminum, magnesium, and what other dopants are going into that lattice. So maybe some effort there with using theorists to help us do that. But it was a logical extension. The more nickel you put in, the higher energy density you can get out.
In a related question on NMC, have you examined the structure of NMC to see if the first cycle loss is associated with some kind of phase change or reordering? And I'm assuming reordering here means the metals on that are alloyed together there.
So far, we've not seen any change whatsoever in the bulk. We have not looked closely enough at the surface to see whether the surface is changing. We suspect it is, but it's difficult really to look at the surface because by that time you've got carbon there, you've got organic solvents there, and by the time you got an electron microscope, it's seen the air, and also the electron microscope itself can cause reactions. So I think my colleagues, Shirley Meng and Yishui at San Diego and Stanford, are planning to try to do some cryo-TEM to look at the surface so it can't change. But we know there's something going on the surface. We don't know exactly what.
Okay. Yeah, there's a related question on this actually. Is there a way to monitor with dynamic in situ imaging what's happening during the voltage discharge and calendaring?
Certainly during the voltage charge and discharge, there's a lot of operando experiments going on both in our labs and many others. So we know exactly what's happening to the structure. The lattice parameters change so the volume peaks initially, then it contracts. As you put, take the lithium in and out. And one of the concerns is if you take too much lithium out, it contracts too much and the crystals, or more accurately, the meatballs, in fact, crack as the single particles expand and contract. So there's an interest now in looking at single crystal NMCs. I know Jeff Dahn's done some of this work. Pacific Northwest National Lab has done some of this work. Has a lower surface area. It reacts less with the solvent. but also because each chrysolite is not constrained by those next to it, it looks like there may be less cracking. So there's some mechanical issues people are working out at this moment. But a lot of this is being done operando so we can see what's going on. And these days, we can do the full cells with really no problems within the beam lines. And it turns out we do a lot of our work now on pouch cells, not button cells. And those are preferred for the beam lines as you got no metal or anything in the way.
I have a more general question now on the connection between academia and industry. We've seen many advanced battery technologies and battery materials now. However, they're rarely used in actual batteries. What is the biggest gap between the academic developments and industrial use?
One of the big complaints I have in this field is that there's too much hype and not enough meat. So quite a lot of the things you'll hear about in academia are not really relevant to a real battery. You'll see a lot of people cycling cells at C rate or higher, in and out continuously. And I think Jeff Dahn was the first one to point out, hold these cells, even if it's only a few minutes at 4.5, 4.6 volts, and you'll see they will deteriorate much faster. So people are, I think, listening to that, and he developed some special techniques where you can measure the Coulombic efficiency to about 4 significant figures. So you can really measure what is happening. Because you need to remember the battery is going to last, say, 1,000 cycles for a vehicle, or probably 5,000 cycles in the grid. That efficiency of operation has got to be more than 99.99%. You can't afford any side reactions. And the other thing is people come up with fancy configurations, which if you look at them are totally unrealistic for volumetric energy densities. So you have to look at realistic configurations. And I think in the early days of the magnesium batteries, it's somehow gotten literature that magnesium doesn't form dendrites. And we and others did searches to find out where that came from. We could never find out. But researchers at Texas A&M show you can form dendrites just as easy with magnesium as with lithium. It wasn't the answer there. So I think what I think if you're in the battery area, you have to do relevant but focused research and just keep in mind what other people have done before you. And I think Jay Xiao and the Pacific Northwest National Lab now have a number of extremely highly cited papers and as to what is a realistic configuration for testing batteries. You can't have like 10 cc's of electrolyte there and 10 times the molar amount of lithium and expect to really see what are the limiting factors. You've got to really cut them all down so you have little excess of lithium. And in a practical lithium-ion battery, cut it open, nothing will drip out because you've got the minimum amount of electrolyte in there. So you need to look at things really in a practical manner.
So I have a question here that's interesting because it moves away a little bit from inorganic materials. What are the prospects for biomimetic or biomaterials as alternative electrodes in energy storage?
I think, again, it depends on the application. I think people are looking at batteries or pseudo fuel cells on your body that will use your body fluids to actually generate power for, say, sensors and other implanted devices. Any of those devices, the challenge is being able to get reasonably high energy densities. So for low energy density applications, they may work in the same thing when people are talking about using organics as the cathode. They may be lower cost, they may allow much longer cycling, but they're not going to be applicable for high energy density applications. Now I should emphasize, we should look at all possible configurations. No, I'm not a fan of magnesium, and I'm definitely not a fan of potassium. It's just too dangerous. But we need to understand the chemistry and the reactions of lithium, sodium, potassium, magnesium, and calcium, so we can optimize the ones we actually want to use. We learn a lot by using larger and smaller cations and the impact of crystal structure. But don't sell, an aluminum-ion battery as the next generation of commercial batteries, because aluminum's never going to move fast enough. But it will teach us something about the materials themselves.
All right. You mentioned solid state electrolytes. Do you feel that this is the biggest challenge right now in actually the safety of rechargeable batteries?
It is, no, it should lead to the safest batteries. But no, if we change the electrolytes and the liquid ones, they may also have improved safety. I think solid state ones, obviously they're going to be much safer for transportation, for use. It's not clear to me they're going to have any higher energy density than the liquid ones, despite what people say. The challenge there is two. One is the interfaces. You've got a solid interface. So whenever anybody tells you they've got a solid state battery that works, don't ask them whether they put any liquid in there. Ask them how many drops of liquid they put on each side of the solid, as it will grease that interface. Because you'll find most of the so-called solid state batteries have in fact a little bit of a liquid or a gel there to make it happen. And the other big question is, how easy is it going to be to manufacture those in very high volumes at low cost? And this is where the roll-to-roll technology of lithium-ion, they make billions of batteries a year. They've got that honed to a fine tune, and it'll take many years, I think, to build a similar manufacturing capability for solid state, or for that matter, for any other system that doesn't use the same sort of manufacturing technology.
Okay. Last question on a fun note. Do you have a fun story when you got the call from Stockholm?
Probably many of you knew I was in fact in Ulm, Germany at a large battery meeting when this happened. So I gave the keynote that morning. I think we had coffee break, then I left the meeting for a few minutes. And one of the co-organizers of the meeting caught me and said, "Stay put. Somebody's been trying to get you for the last 20, 30 minutes. Just stay there." And a couple of minutes later, she handed me her cell phone, and it was a member of the Chemistry Nobel Committee who told me, "You've won the Nobel Prize." And she said, "You didn't seem particularly excited." I said, "I was more shocked than anything." And it took me several minutes to realize what it was all about. She said, "You then smiled and seemed happier." But they also said, "Don't say anything for 30 minutes because we're not ready to announce it yet." I then went back in the lecture hall, and I think the last speaker was just finishing. They let him finish, and then whoever was on the stage at that time then announced it. He must have had his computer on at that time. And in fact, before I really stepped out of the room afterwards, Reuters and AP were already there with their cameramen to take pictures. So it really went wild straight away. But I was fortunate, at least I wasn't waking up at 5:30 in the morning. It was like 11 o'clock or 11:30 in the morning in Ulm. And the other big advantage is when I went back from Frankfurt to Newark, Lufthansa put me in first class, because I think I was on the front page of their main newspaper that morning.
Awesome.
So it was busy ever since then, and my life really changed ever since then.
Well, thank you for taking time from the busy schedule to come visit us today here at Maryland. We really enjoyed your visit and your lecture. I'd also like to thank the audience for joining us this afternoon. I'd like to thank 3 people from CMNS, Abby Robinson, Jess Wilk, and especially Sherry Meadows for helping organize this event. And I especially want to thank Dr. Tobin Marks for his sponsorship, for starting this awesome lecture that we hope to continue every year. And I'm glad we were able to do it at least virtually this year. Hopefully next year we can all meet in person. Thank you so much for coming.
Yeah, let me thank you all for inviting me. It was a great honor to be the inaugural speaker in Tobin Marks's endowed lecture. Thank you, Tobin, and thank you everybody at Maryland.
Super lecture, super arrangements. Couldn't have been done without Sherry and her dedication and passion to this project. So everything worked out great.
Thank you, and we hope you enjoyed your visit to your alma mater as much as we enjoyed hosting you, Tobin.